So yeah, so you might think, okay, if you're moving at constant speed, then why is there acceleration? But obviously you're changing direction as you're moving in a circle, so there's acceleration from that. Now, in general, you may ask, okay, what if v is a function of time? What's the formula there? You can do it in terms of tangential acceleration, radial acceleration, so on, and maybe it's good to learn that at some point, but I would suggest if whenever in doubt about these kinds of things, there's a very simple way where you can just say that if v is a function of time, then you have theta of t, for example. That's the angle you are on the circle. And then therefore you have x of t is equal to r cosine theta of t. And then you can compute the accelerations of x and y or something like that. All right. Anyways, but the other so I guess this is what you can do in general, but still the result to know is that if you have if you're moving and v is accelerating, then and v is changing, then you will still have an acceleration. This is a radial acceleration, v squared over r. And then you'll have a tangential acceleration, which is just equal to v dot. So in general, if v is changing, then you still have the same v squared over r instantaneous radial acceleration pointing towards the center. And your tangential acceleration is simply the derivative of velocity. So that's circular motion if you're not going at the same speed. And then finally, there's one more sort of fact which I guess is used in some problems, which is that if I have like a circular hoop and I have a bead attached to the hoop, and the bead slides down due to gravity, and eventually it's set somewhere here, then the speed of the bead is just root 2gh. This is h. But the bead slides down, and this is just by conservation of energy. And then in general, whenever you have circular motion and you have these accelerations, we usually combine it with second law. So if the problem has some forces, like let's say you're swinging something around and there's a tension, then the tension use F equals ma. Or if you're like falling down a hoop and there's a normal force, there's a gravitational force, and those combine to provide the acceleration. So it's just like normal dynamics, except that the accelerations are a little bit funnier because you're moving in a circle instead of in a straight line. And somebody asks, will in any case become an SHM then, a simple harmonic motion? Not really, because simple harmonic motion is a linear motion. Simple harmonic motion only moves in one dimension. Circular motion is in two dimensions. And the reason you might be thinking of this related to simple harmonic motion is that if you take uniform circular motion, so the same speed, and you project it onto a line, then it looks like simple harmonic motion. But that's actually not too important. You should think of like circular motion is a two-dimensional motion, simple harmonic motion is a one-dimensional motion. All right. So that's basically it for like the quote-unquote theory. There really isn't much theory. It's just a lot of problems which have a similar flavor. So before I get to the problems, are there any questions about anything I've said so far? No questions? All right, let's get started to the problems. All right. So this problem, what do we have? So we have a hoop. And the hoop is being spun around on its vertical axis by omega. And then we have a bead here. And again, the radius is r. And the angle is theta. And there's no friction. So the question is, what must omega be such that this bead does not slide up or down the hoop? That's the question. So I'll give everybody like a minute to think about it. All right. So so note that vertical acceleration of bead is what? So can somebody tell me what the vertical acceleration of the bead is? Zero, yeah. Okay, here's a harder one. What is the horizontal acceleration of the bead if it's at rest? Or if it's not moving up or down the hoop? It's obviously not at rest, but somebody says mr omega squared. That is incorrect. It is not mr omega squared. So the question is, what trajectory is this bead tracing out? Mr sine theta omega squared, exactly. So the reason for this is that if you look at this bead and you look at its trajectory, it's actually moving on a circle of radius r sine theta as it's spinning around. So the trajectory of the bead is a circle of radius r sine theta, which means that the acceleration is mr sine theta omega squared pointing towards the center. Let's say to the left. So this is a bit tricky. It's on a circle of radius r, but the trajectory of the particle is on a circle of a different radius. So the only thing that matters when finding the acceleration of a circular motion is what trajectory that particle is on. Because acceleration is a purely kinematic quantity. It just depends on how the particle is moving. So in this case, the particle is moving in a circle of radius r sine theta. All right, so this is, I guess, the trickiest part of the question. Now the rest of it is just standard Newton's second law stuff. So let's just go through that really quick. So I guess you have a normal force and you have mg, right? So since the vertical component is the vertical acceleration is 0, we must have n cosine theta equals mg. And then the horizontal component, we must have n sine theta equals m So what does this mean? This implies that omega is equal to if you just solve it, I think this is what you get. So the omega you need is root g over r cos theta. Is this clear? All right, so here's the question. What is omega as a function of theta? Like, what is the minimum value of omega for theta? Can somebody answer that? What is the minimum, according to this answer, what is the minimum possible value of omega? Yeah. So it's square root of g over r, which means that it's not 0. So what happens if I spin the hoop with omega less than root g over r? Can somebody tell me? Hmm? What? The bead slides down. Yeah, so exactly. So what happens if you spin with omega less than root g over r? It'll eventually just sit at the bottom of the hoop. Yeah, it will not go through circular motion. Exactly. It'll have some sort of oscillation. Like, it's not possible for it to be in circular motion. And what happens if theta is equal to pi over 2? What does this answer do? I'm just going through this because this is useful for physics problems when you get a funny answer or just any answer. It's good to check limiting cases. So what about theta equals pi over 2? Okay. And the reason for that is that if you spin it really fast, it's not imaginary. It's just infinity for theta equals pi over 2. But if you spin it really fast, it's not possible to keep it purely horizontal. And of course, it's not possible to keep it more than that, if you think about it. So this sort of answer is telling us that it's only possible to keep it between 0 and pi over 2 if you spin it. Anyways. Okay, so any questions about what I did here for this problem? The last part of it. So here I'm using this, I'm combining this with Newton's second law. The vertical force is n cos theta minus mg. That's the vertical force. And the horizontal force is n sine theta. So then these are just statements of Newton's second law for vertical and for horizontal, respectively. Any other questions? Can omega reach a value of infinity? Well, all that means is that it's to keep like omega reaches infinity at theta approaching pi over 2, which just means that if you want to keep the bead at pi over 2 and hold it there, you have to spin the hoop really, really fast. That's all it's saying. And if you think about it, like, anyways, yeah. So just try to imagine you have to spin the hoop really, really fast to keep it close to horizontal. All right, if there's no more questions, let's move on. So let's look at.
Hello, are we allowed to speak? Another question.
What's the question?
Yeah, like, are we allowed to speak?
Yeah, sure.
Yeah, I had a question. Like, can we consider like theta to be very close to, like, less than equal to one, like very much less than one? I meant to say. So we can
Uh,
approximate r sine theta is theta.
no, I mean, I think this problem wants you to do it in general with any general theta, but also there's no real benefit to making theta really small unless you want to do some sort of oscillation thing where you're not doing pure circular motion, like if the bead is going to sort of oscillate because it's not able to stay stationary. In that case, maybe it would be easier to approximate theta to be small, but for this simple problem, there's no reason to do that.
Okay,
Okay.
thank you.
Yeah. All right. So problem 2. Also, yeah, by the way, if you have any questions, feel free to unmute and ask your question by speaking. I'm always okay with that, and I appreciate that. All right. So the next question is a kind of interesting setup. It's a funny setup, but if you just keep your head straight and just follow the principles of this is the acceleration, these are the forces, use F equals ma, then it should be doable. So what do we have here? So we have a frictionless pull, just some sort of like stub, some sort of pull, and what we have is some string that wraps around this pull partially. This is my so and what happens is that this is a bad drawing, but whatever. So what happens is you're pulling here, and the radii of these things are R and big R. So what you have, you're sort of pulling on one end of the string, and there's a mass m here, and it's moving along in this circle. And initially, it has tangential velocity v0, and you have to pull it in such a way, like depending on how you pull it, you have to pull it in such a way that it always keeps moving in a circle. And if you do it like this, so you pull such that m moves in a circle of radius r. What is speed of m as a function of time? So it's a bit of a strange problem setup, but hopefully it makes sense. All right. Can everyone hear me? I think I got cut out for a second. All right, great. Okay. So how do we get started on this problem? So there's some tension force in the string, right? Yeah. And tension is the only force on this thing because this is a in the plane, in the horizontal plane. So there's no gravity. So tension is the only force. Now we know that the radial acceleration equals v squared by r, and the tangential acceleration equals v dot, if v is changing as a function of time. So my question to you is, what is the radial force? What is the radial force on this mass? Yes, yes. So people are giving yeah, exactly. So exactly. So people have given the answer. So somebody said mv0 squared over mv squared over r. That's not correct because or yeah, no, mv squared over r is correct. But that's what we're going to set it equal to using Newton's second law. So what is the force coming from the tension? So people answered that if I define theta equals sine inverse of little r over r. So theta is this angle right here. Then I have, for example, t cos theta equals mv squared over r. This is the radial F equals ma equation. And then similarly, the tangential acceleration is t sine theta equals mv dot. Shouldn't t be the hypotenuse? No, t is a force. T is not a length of the string. The lengths of the string here are, this is r, this is little r, this is capital R, and this length is the square root of capital R squared minus little r squared. T is just the tension force here. All right. So so the right angle is right here. This is the triangle. Okay. All right. So now the problem is purely sort of a just a sort of differential equations kind of problem. What is v as a function of time? But sort of if we eliminate these, we can get that rv dot. If I just divide the two equations, I get rv dot over v squared equals tan theta. The right angle should be at the center. No, the right angle is here. This is the string is tangent right here, because this is the pole. This is not a right angle. Hopefully that makes sense. So if we eliminate the tension, we get that this is our differential equation, and here tan theta again is going to be like, I guess, like little r over the radial force is t over cos theta. Ah. No, No. The radial force is T times cos theta. Because the tension force is pointing this way, so its radial component is just T cos theta. Like you have the tension force and you're splitting it into a horizontal component and a vertical component. Hopefully that makes sense. All right. So we have this. And if you just solve this, you can just get like dv over v squared equals tan theta over r dt. So if you integrate this, you get 1 over v0 minus 1 over vt. So v of t is something like anyway, this is the less interesting part of the problem. The more interesting part is up here, the forces. All right, so I think people are getting confused. So t is not, why is t proportional to the length of this triangle? There's no reason to assume that. This triangle is just a geometric triangle. Like when you have a vector force, if I have, these are my axes that I want to split onto, and I have a vector force, then let me draw in a different color. If I have a vector force like that, then its horizontal component is that, and its vertical component is that, where these form a rectangle. That's always the case. So in this case, I have a tension force right here. So its horizontal component is just tension times cos theta. Does that clear it up? Well, there is a right angle here, but that's a geometric right angle. I think the thing you're getting confused about is the fact that this tension is not a length. This is a force. This is a tension force. It has nothing to do with it's in the same direction as a string, but has nothing to do with the length of the string. This is a geometric right triangle. And if you split the tension, you have a little sort of force right triangle here, which you use to split the forces. All right, it's good. This is a point of confusion, and this is why the geometry of this question is a bit tricky. That's why I say if you keep your head straight. Okay, somebody else asked the exact same question. The radial force would be T over cos theta. That's what I'm trying to explain right now. The radial force is T times cos theta. If I have a tension force in this direction, then its horizontal component is just T cos theta. I mean, think about it. Like if I have a force of 10 newtons, how can one of its components be more than 10 newtons? That makes no sense. If I have a force of 10 newtons, then any of its components has to be less than 10 newtons. Because the components, so T over cos theta would not make any sense. If I have T in this direction, the radial component is T times cos theta. Again, you're getting confused because there's another different right triangle here. But this right triangle that I drew is a purely geometric right triangle. And the tension is not a length of the triangle. The tension is just a force which points in the same direction as one of the legs of the triangle. But that's just because there's a string there. All right. Hopefully that makes, so good. These are the kind of questions I want to field because this is a very, in principle, this is a simple problem because there's just one force and there's just some acceleration, but it's very confusing because that's what I said. In circular motion problems like this, you have to keep your head straight. Just say, okay, this is the motion, these are the forces, and just set the accelerations equal to the forces. And it should work out. But yeah, so good questions. All right, any more questions? Looks like there's a lot of questions on this one, which is good. So I'll give it another 30 seconds to see if there's more questions. All right. Looks like there's no more questions, so let's move on to the next problem. So the next problem, it's nominally a problem about circular motion, but it turns out that the actual trickiest part of the next question is dealing with friction, dealing with the difference between static friction and kinetic friction, and thinking about that carefully. So this is a point of, I remember last time when I taught 2 weeks ago, this was a point of confusion then as well. And so will probably be a point of confusion now as well. And how to deal with friction correctly, especially when you have static friction. Because kinetic friction is relatively easy. If you're sliding against an object and the normal force is N, then the friction force is N nu pointing opposite to the sliding. But if you have static friction, then what is the value of the frictional force? That's a pretty big confusion point for people. So hopefully with this problem, we can talk about that and clear up some of the concerns people have. All right, but there is also a somewhat tricky circular motion aspect to it. So what we have is we essentially have what's known as a banked track. So essentially what a banked track is that this is my car. So this box is a car. And its velocity is sort of pointing out of the page. Does everybody understand this notation, by the way? This is a very useful notation in physics. So let me just clarify what this notation is. It's like if I want to draw an arrow, but I want to draw an arrow which is not in the plane, then what I do is this arrow is the arrow pointing out of the page, and this arrow is pointing into the page. So this is just some notation to draw arrows which are not in the plane. All right. So a bank track means that what you want to do is you want to imagine that this sort of thing is sort of made into a circle. And the car is sort of, so imagine a race car, right? It's going in a circle, but the circle has an incline of theta. That's how you want to imagine this. All right. So and the radius is r, which means that if the center of the track is here, then this radius is r. So is everybody clear on what the circular motion is here? Because the way I've drawn it, it looks like there's no circular motion. So it's very important that you get the picture of the circular motion in your head. So if somebody does not understand the circular motion picture, then just ask it in the chat. Because without that, it's going to be very unclear what's happening. All right, so nobody is saying that they don't understand it. So hopefully everybody understands what's going on here. So the question is, now this plane has friction. find min and max speeds for a car such that it can go without slipping. All right. Just imagine if the car is not moving if the car is not moving at all, it's not moving in a circle, then it's just going to sit there and just slide down the inclined plane because there's no circular motion. So if the speed is 0, it'll just slide down. Well, it'll slide down assuming that tan theta is greater than mu or something. Assuming that the angle is enough, then the car will just slide down. If tan theta is less than mu, then you can have the minimum speed be 0. So this will, by the way, be a good check for our answer. Is that when we find the minimum speed, then for tan theta less than mu, we should find that the minimum speed is 0. All right. So let's solve it now. So in our free body diagram, what do we have? We have gravitational force, mg. We have normal force, n. And we have frictional force, F. Now, do I know a priori which direction F is going to point in? And do I know the value of F? Can somebody tell me what direction F is and what its value is? The value of F is v squared over r. That doesn't make any sense. Somebody says F equals mu mg cos theta, and that's not correct. But that seems like it would be, but the setup in this problem is very different. The acceleration of the car is not down the plane, so it's not mu mg cos theta. All right, good. So it looks like there is a lot of things we need to talk about, which is what I expected. Still not, because so you'll see the normal force is a bit funky in this problem. We'll get to it. So a priori, we actually don't know the direction of F, and I'll just draw it as pointing up the plane, but it may be pointing down the plane. The only thing we know is that minus n mu. This is the only thing that static friction tells us. This is the statement of static friction. That the friction is between minus n mu and n mu. So people are giving various formulas for F, and they're actually all wrong. And the problem is, it's pretty complicated. So they're like, we'll have to solve it and write down the more complicated formula. So it was more like a trick question because I thought people would just say n mu or something like that. And the point is that I'm trying to. Hello? Can people hear me? Somebody told me I'm not audible. Hello? Okay, good. So the point is that the only thing that static friction tells you is that the frictional force is between minus n mu and plus n mu. That's the only thing you know. This is a very, very, very important concept. Because static friction only tells you a range for F. And F can take any value in that range. Can even be 0. But kinetic friction always is an exact value. Is this clear? This is a very important concept. So I want to make sure that this is clear. Okay. So now this is the friction part. Now the circular motion part is also a bit confusing. Based on people's responses, like, yeah, it's also a little confusing. So can somebody tell me the direction of the acceleration vector of the car? Just the direction of the and if you want, you can tell me its magnitude as well. So in terms of horizontal and vertical, so like just regular horizontal and vertical. Okay, good. No, somebody said v squared over r cos theta. That's not correct. Good. So in this case, the acceleration is purely horizontal. And its value is just equal to v squared over r. Because it's moving in a circle of radius r. Circle of radius r and speed v. That's literally it. Acceleration is pointing inward with v squared over r. Is that clear? So now what are why is the center of rotation not on the ramp? Okay, so somebody asked this, and this is why I was asking if the setup was clear. The setup is that this is imagine a really, really, really large radius circular track. So I have some racetrack, which is a big circle, right? But now imagine that the rate that the track is inclined upwards by angle theta. The center is really, really, really far away from the track because it's a really, really large track and it's just inclined upward by angle theta. Okay, cool. Yeah, hopefully that's clear. Otherwise, the geometry won't make sense and these accelerations won't make sense. All right. So so now the vertical F equals ma equation tells us that n cosine theta plus f sine theta. Is that clear? I'm just balancing the vertical forces because there's no vertical acceleration. Horizontal just says that n sine theta minus f cos theta is that clear? All right. So I guess to simplify or to make this somehow like a little easier to deal with, let's define R to be F over N. So R is this ratio of friction to normal force. And again, the only thing I know is that, and then the goal is to, and then we'll sort of solve for V in terms of R. Oh, R is a bad choice. R looks like a radius. Let's call it K. Solve for V in terms of K, and then minimize and maximize V as a function of K. Where K is in the interval minus mu to mu. Because there's a range of velocities, there's a range of speeds which work according to the problem. So the only restraint is that this ratio k must be between minus mu and mu. So we have to use that to figure out what the maximum and minimum velocities are. So let's solve for it in terms of k. So what do we have? We have like n times cos theta plus k sine theta equals mg, and n times sine theta minus k cos theta equals mv squared over r. So this implies that v, if I divide these two equations to get rid of the n, so here's so now based on this, what is the minimum speed? Somebody tell me the minimum speed. So this is v as a function of k. And the only thing we know about k is that it's between minus mu and mu. Not necessarily 0. Okay, so so let me just say v min equals 0 if tan theta less than equal to mu, because then you can just take k equals tan theta and make this 0, and v min equals because it's best to just take k equals to mu, because the numerator decreases and the denominator increases when I make k closer to when I make k bigger. So the minimum is just when k is as big as possible. And actually, what we're seeing in that case is that in the minimum speed case, the friction is actually equal to n mu, pointing all the way up the plane. So you could say, hey, in fact, if you had written f equals n mu pointing up the plane, and you solved it, you would have got the correct minimum speed. But that was purely luck. You know what I'm saying? Only thing you know is that it's between minus mu and mu, the ratio of friction to normal force. And it turned out to happen that the minimum speed happened when friction was actually equal to n mu. But that's more or less a coincidence. The fact that this function was minimized when k equals mu, or when friction actually equals n mu. And similarly, what you can do is v max equals infinity if tan theta greater or equal to 1 over mu, and v max all right. So this is quite a tricky problem for various reasons. Friction aspect, circular motion aspect, and then sort of this final aspect with optimizing v. So are there any questions about this problem? Oh, sorry, I forgot the root gr term in all of these. Any questions? I think this is quite a tricky problem, so either people are completely confused or everybody followed exactly what I said. And I don't think that everybody followed exactly what I said. So if you have any questions, please ask them. And it can be about any part, the basic setup, any step I did, or anything like that. Please ask the questions. Yeah. Every term, I just forgot the root GR term. It must be there by dimensional analysis, and I just forgot to copy it from here. So why are there cases? So let's look at the minimum velocity. So what I know is that k is in between minus mu and mu. So if I'm trying to minimize this thing, and obviously let's say v has to be positive, then if tan theta less than or equal to mu, I can just select k equals tan theta, and then the v min is 0. So if tan theta less than or equal to mu, then I can just select k equals tan theta, and then I can make the v 0. So there is a scenario in which you can just be staying on the ramp without moving at all, and you won't slide down. And that's actually very obvious, because if I just stay on the ramp with no circular motion, just stay on this inclined ramp, and tan theta is less than or equal to mu, then that's the sort of standard thing. This thing won't slip down. It's a well-known result. But if tan theta greater or equal to mu, then I can't select k equals tan theta anymore. And then the way to make the v as small as possible is to make k equals mu, because then the numerator is as small as possible and the denominator is as big as possible. The point is, if tan theta less than or equal to mu, it is a scenario in which v equals 0 is valid, and this thing won't slide. But if tan theta bigger than mu, then I have to have some velocity to make this thing not slide, and that's just when I make k equals mu. In this case, that's a small speed that would work. Similarly for this problem, this part, if tan theta bigger or equal to 1 over mu, then I can just take k equals minus tan theta, or minus 1 over tan theta, something like that, and make this thing infinity. And if tan theta less than or equals 1 over mu, then the maximum velocity I can take is just when k is minus mu. So somebody asked, the thing is, we considered one case to be less than or equal to mu and also greater or equal to mu. Why not only greater than mu? Okay, I mean, maybe, like, are you just saying if I just make it like this, is that better? Okay, by the way, so that's a valid point, but it's actually not a valid point, because in physics, these things don't matter. Like, you never care about the exact, if b is exactly on the boundary, because it's physically, it's never going to be exactly there. It's either going to be slightly lower or slightly greater. So in practically, this is not an issue, but yes, technically you're right. That, I mean, okay, actually, I would say technically it's not right, because really there's no just like there's no case when tan theta is actually exactly equal to mu. In physically, that's never going to happen. It's always going to be either slightly less or slightly more. So in physics, we never care about, in physics, we could put greater equal to here, we could not put this here. They're all the same in physics. In fact, there's a funny story about the International Physics Olympiad about this, but I don't have time for that right now. So we can talk about that later if you want to know. Where somebody got penalized for not putting the correct less than equal to versus less than. Anyways. All right. Okay, problem 4. Okay, any more questions? I think this one's also relatively tricky. So any other questions about this one? All right, let's move on to problem 4. So in problem 4, problem 4 is actually a very similar problem. So what do I have? I have a unicyclist. And the height of this unicycle is as h. And the angle is theta. And there's again, this unicyclist is moving in a track of radius r, but let's say velocity outward. So the unicyclist is going in a big circle, but leaning inwards a little bit. So what omega must the unicyclist have? Or I guess not omega in the, we'll just call it v because that's kind of a similar question. You know, you're moving in a big circle and you're leaning inwards a bit. In the previous case, it was a bank, like the track was bank. In this case, you're leaning in a little bit. Similar setup. What speed must you have in order to be stable in this track? So I'll give everybody like a minute to think about it. So this is actually a bit tricky question. We might need another concept for this. All right, that's fine. We can do this. All right, so any ideas? Yeah, somebody says we need to balance torque, and that's correct. But the problem with this is that this thing, that the torque, you can only balance, you can only do rotational stuff when the point of contact, or like when it's, because the problem is this thing is moving in a circle, so it's much more complicated. So this is an idea I haven't talked about here, and I guess I didn't realize that we need to use this, but that's fine. We have to work in a rotating frame. Now, I think this is covered later in the physics circle, this concept of working in accelerating frames of reference. So if you don't already sort of understand how oh no, looks like I'm frozen. Hello? Am I audible? All right, so we have to work in a rotating frame of reference, which is always very confusing to deal with. In general, I would recommend to not work in rotating frames of reference, but in this problem, the working in a rotating frame of reference is necessary, I think. So what happens in a rotating frame of reference? So in this case, now unicyclist is at rest. And what are the forces on the unicyclist? Well, there's gravity. Let me draw them in blue. There's gravity There's normal force. There's frictional force. And now there's this, actually it's centrifugal. There's this fictitious centrifugal force. So in the rotating frame of references, there's these fictitious forces. So there's a sort of centrifugal force pointing outward. And I guess in this case, we would want to just say v squared over r. And you can sort of view it as if it's acting on the center of mass. So now in this scenario, we have to balance torques, and we're going to balance torques about the pivot about this point. And then what do we get? If we call the length L, or it's H. So what we get is that mg h over 2 sine theta minus so v equals root gr tan theta. Does this make sense? So don't worry too much about centrifugal forces and fictitious frames. This is what's known as a centrifugal fictitious. And the only reason this exists is because we're working in an accelerating frame of reference. Why didn't we work in the inertial frame? Yes, I really wanted to work in the inertial frame, but in the inertial frame, it's very hard to quantify the notion of the fact that the unicyclist stays at the same angle. Because what's going to happen is if you move with the wrong velocity, the angle of the unicyclist will change. He'll either start falling inward or he'll start, getting more vertical, depending on whether the speed v is too high or too low. But that's very hard to quantify. Like that's very hard because the unicyclist is also moving along in a circle, so its sort of angle is very hard to talk about in the sort of frame where he's also moving in the circle. What is his sort of the orientation of his body? It's very hard to talk about that because then there's a sort of there's a rotation acceleration plus the acceleration of him moving up or down or something like that. So it's very hard to do torques when the entire object is accelerating. So, but that's why if we work in the rotating frame, we can view it, we can think about it as if the unicyclist is at rest, but there's just this extra fictitious centrifugal force. That's why we have to work in the, that's why I realized that this problem is not the best, because this problem really is about fictitious forces. Because any logic you do in the inertial frame is very it's either very complicated or it's basically wrong, because you can't do torques on it's very hard to talk about torques on an object where the point is accelerating. You can do it. I'm not saying it's not possible. I'm just saying you have to be very careful. And this goes more into like issues of angular momentum and fictitious forces and more complicated rotational topics, which I'm not covering right now. So this problem actually is a problem in more advanced topics. Anyways, but hopefully this gives you a taste of some of the fictitious forces things that come later. All right. I guess let's move on to the next question. So this is a question from the F equals MA. All right. Okay. So this problem, what do we have? So what you have is you're swinging around a mass of some value, string of radius r. But practically, when you swing around a mass on a string, what you're doing is you're rotating your wrist at some smaller radius, right? So in reality, your wrist is moving at a smaller radius. And this is capital R and this is little r. So in this problem, I think r is equal to 2 meters and little r is equal to 3 centimeters. So we can kind of assume little r is much, much less than capital R. And then they're saying that the phase is off by pi over 2. What that means is that if you think about it, your hand is the angle of your hand is this way, and the thing you're swinging around is that way. Because your hand, yeah, if you just look at the diagram, that's what it means for them to be off by an angle of pi over 2. So the question is, estimate the force of air resistance on the object. So you're swinging around at constant speed, but somehow there's an air resistance. So you're adding energy into the system to compensate for air resistance. So the question is, what is that force of air resistance if you're able to swing it like this? So the first question is like, yeah, so any ideas? Air resistance is proportional to v squared. Yes, but we don't know anything about the geometry of the mass, so we can't use that. Yeah, so we have to use something related to energies. So remember, this is actually like the problem we did before. And in this scenario, we should be finding that the speed is increasing. If you swing it in a circle, you swing your hand in a circle, then you are actually adding energy to the system. And if you go back to the problem where we're sort of swinging around a pole, which is a very similar setup, that pole is like the radius which your hand is swinging at. We saw that the speed was increasing in that case. But in this case, we're told that the speed is constant. So somehow the speed should be increasing in this situation. And the reason the speed should be increasing is basically because the tension force is not actually pointing towards the center. There's a component of the tension force pointing towards the center, but there's also a component of the tension force which is tangential. Because if I made this, let me actually, for sake of demonstration, make this a little bigger. So imagine you're swinging your hand at this radius. Then the tension force is not actually pointing towards the center of the circle. So there's a component tangential. So this is actually increasing the speed of the object. But we're told that there's no tangential acceleration. So actually we don't even need energy. So can we just solve this using this idea? So what is the so we know tangential acceleration equals 0. So there's some air resistance. And what is the other tangential force? Can somebody tell me the tangential force due to tension? Very similar to this problem we did before. So if I define this angle to be theta, it points along the string. However, the string is not pointing towards the center. The string is pointing towards this point on this circle of your hand. So the other component is essentially, it's approximately, if we use small angle approximation, it's TR over R. Yeah. And there's some confusion about whether the right angle is here or here. And like this comes out to what we were doing before. But in this case, since R is very small compared to capital R, it doesn't really matter. Anyways, but the point is that the force is about T times little r over R. And you know this must be the air resistance force. And again, we're assuming little r is much smaller than capital R. I'll just call it F, not F sub A. It's more confusing. But then we also know that T has to be m omega squared R, because if you just zoom out, that this tension, it's actually T cos theta, but since theta is very close to 0, the tension is m omega squared R. So this implies that the air resistance force is what? M omega squared little r. So what is this in this problem? This is 0.1 kilograms times 100 radians squared per second squared. Or I guess just say per second squared, because radians are dimensionless. And little r is 0.03 meters. So this comes out to 0.3 newtons. All right. All right, let's move on to the final problem, and then we'll finish. So in this problem, what we have is it's an interesting. So we have a vertical loop, and the mass is attached to a rod L, and it moves, and it's swung around, and swung around with period t. So no longer tension, but the period is t. So what is the difference in tension in the rod when it's at the top and when it's at the bottom? So can somebody tell me why the problem had a rod and not just a string? Why can't you spin it around the string? Exactly. String can't hold compression. The rods can hold compression. So basically this tension force we solve for may be negative. Anyways, so let's say the tension at the top is F1. And the speed at the top is V1. Then I know that F1 plus mg equals mv1 squared over L. And then at the bottom, let's say the tension is F2. It's also mg. And the speed now is v2. Now I know f2 minus mg is mv2 squared over L. So f2 minus f1 is 2 mg. But now the question is, what is the difference in the squared velocity from the top and the bottom? Does somebody know how to do that? So we can actually use conservation of energy. So this is what conservation of energy says. So v2 squared minus v1 squared is equal to 4gl. So f2 minus f1 is actually equal to 6 mg. So it's not dependent on the period t, which you actually could have known from dimensional analysis from the start. Couldn't have been dependent on t. All right. Any questions about this? What if we just work with a change of potentials? I mean, that's what we're doing here to find the conservation of energy equation. So I'm not sure what you mean by that. Anyways, okay. If there's no more questions, then then we'll end for today, and we'll see you next time. So have a good week. See you. Bye.